Okay. How are you guys feeling on a Thursday afternoon? Very good. So today is going to be a nice shift of pace. I mean, we're going to look at a completely new topic, more on decisions, which, at the end of the day, you can make all sorts of predictions, but you want to make decisions based on them. So we'll look at a few ideas related to decision making. And so it'll be a nice switch from all the unsupervised and supervised learning models that we've been looking at. Okay. So this was the list of topics, at least in the objective of this course on syllabus page. I think we have mostly covered all of them, maybe not GPT-3, BERT briefly. So what we have not covered is specific optimization related details. But they're all first order methods, by which I mean they use gradient information. So we've discussed some details about gradients at the very beginning of the course. So this is a list of topics related to mostly neural networks. And so what we're going to do from this lecture onwards is to try to take a tangent and then again come back to merge it back with deep learning in a couple of lectures later. Which is the tangent is going to be, okay, let's look at basics of some decision making concepts. Okay, not, decision making is a huge area in itself and a lot of variations there, but look at some ideas in decision making, and then we'll merge it back to some neural network architectures that we've seen, which can also underlie such decision making ideas. Okay, and in particular, the phrase is going to be reinforcement learning, but we'll not get there. At least the details will not get there, at least for a couple of lectures. Okay. So the most important thing to realize is that we are getting very close to the end of the course. Today is this session, and after that, effectively there are 3 lectures, after which there is a Thanksgiving, which kind of occludes with our meeting session. And so we only have 1 session after that, I think. So what I'm proposing, and I'll send you guys an announcement, is next lecture we can try to again focus on projects. Okay. What I've seen historically is that if I don't give feedback, then it just it's kind of hard to know what pace you're in, what trajectory you're in, and whether you will get to where you want to be. I mean, where you want to be by the end of the term, you've already at least made 1 attempt at kind of projecting it in your intermediate report, but it's good to have some checks. So potentially next lecture we'll try to do that. So I'll let you guys know by an announcement. But that doesn't really. So what does it affect? It's we're still going to be in this trajectory of decision making and then merging it back to neural networks. Maybe some bits and pieces here and there I'll kind of discard in this discussion. Okay. But it doesn't affect the overall flow of what we're trying to do. Okay. Great. It's also, I guess, feels great to not have assignments because otherwise there should have been an assignment, I guess, next lecture, which is to be submitted next lecture. You're not submitting it, but I really suggest have a cadence. Those hours you blocked previously, you should continue to use those hours and maybe more hours for your project. Okay. As I said, we are gonna look at, just discuss some ideas which are a little bit different from supervised learning that we've been seeing, in other more primary courses as well as the earlier part of this course. Okay, and we need to kind of reason why do we need some new vocabulary and new techniques. Okay, not just for decision making, but also you'll see that there's going to be some close parallels with supervised learning, and then you say, why can't I just use supervised learning, and why do I need this more fancy thing? So we need to kind of get to that root, understand what the differences are. Okay, so that's the lecture for today. And then, as I said, later on there's going to be some ideas on reinforcement learning, which is a specific type of decision making process. And then we'll try to get to what is called deep reinforcement learning. The deep part obviously corresponds to a deep neural network part of that decision making paradigm. Okay. And actually, there's a book, Reinforcement Learning and Introduction, which is a very nice book to have a look at, just like the other books. But it really depends on what your emphasis is on to pick up any of these books. actually dive into deep learning is very, very comprehensive. It actually gives you not just PyTorch, but also TensorFlow and other couple of other foundational, I guess, packages to build neural network models. So it's very, very comprehensive. So if you really like something, a description discussed with a code example, then it's a good book to look at. Okay, so this slide, but let me get to what the goals would be then for today. Is really there are 4 goals. Firstly, what is online learning? And how is it different from supervised learning? Okay, so this is mostly at the qualitative level. It's not going to be anything concrete, but just appreciating what is this new, slightly new spin on learning, right? And then I guess this is not really a big goal, but basically relations between forecasting and decision making. You can, you could say that whatever I'm predicting, that could be the prediction itself could be a decision that I'm predicting, but it's not always the case. So we'll briefly comment on it. The majority of the lecture today will be about kind of motivating towards this idea of online learning. So particular simpler problems. There are still problems which are part of what is called reinforcement learning, but today we'll not really talk about the bigger hammer or the bigger umbrella decision making. We'll look at some simpler instances. They're called, and we'll disaggregate the name. Okay, one of them is called multi-armed bandit problem, and the second one is called a contextual bandit problem. So we'll look at what these are, and they are basically tied to something that you can gain by doing online learning. Okay, that you cannot gain by, that you might be inefficient in doing if you were just doing supervised learning. There's going to be some gap, and these two, I guess, versions of the problem address those gaps, at least define those gaps, and then there'll be solutions which address those gaps. Okay. No. What? So Adobe. No. How do you open this in a thing? No. Is there? Okay. Yeah. So let me go back to a couple of slides. So as I said at the beginning of, I think when we started the course, I said there's 2 buckets of major themes. One was about using deep learning tools, and the second one was about decision making. And I was using the word complex decisions, but we'll see what these decisions are and why they could be complex or hard. Okay. So we are kind of entering the second bucket, which is the decision making setup. And so there are many ways to make decisions, and we're going to look at only one way here in this course. So it's just one example sampling of how to tie predictions to decisions. And in terms of the trajectory, as I said, we'll look at online machine learning today, which you can think of it as a simpler version of reinforcement learning. It's actually, reinforcement learning can also be considered as online learning. People don't use that word, but we'll look at some simpler instances of reinforcement learning, if you want to call it that, and then hopefully that connect decision making back to neural networks in the third part of this portion of the course. Okay. So decisions, right? So there's just a general commentary on decisions. So many times you could repurpose your supervised learning model to make a decision, directly make a prediction on a decision. For example, you could say, this is a little bit of a contentious example, but if you want to say, hey, somebody is you want to okay, let's say somebody wants to be what's it called, approved or denied a loan. Okay, so just it's a problem which has lots of angles to it, including ethics. But if you are doing prediction of if you're trying to decide to give somebody a loan or not based on their credit history and all that information, you could directly predict, use a model which would predict a binary thing where you could say approve or deny, for example. Okay, so the model itself is directly kind of predicting something which is itself the decision. So there's no further processing that you need to do to make the decision. Okay. And this is not just for approval denial type of situations, but there are many other situations where the prediction itself, okay, tomorrow's whether as buy sell signals or something, you can in the stock market, for example. So you can actually massage your data in such a way that whatever you're predicting, you can think of it as, okay, the algorithm is suggesting a decision for us directly. Okay, but it turns out there are problems where you can't directly map. There's no simple mapping, as in a simple transformation or a simple function which goes from the forecast to the decision or the prediction to the decision easily. Okay, and one typical canonical example is let's say inventory management. I mean, there are many other types of problems like this where the forecasting or the predictions, generally there are multiple predictions, and then you have to merge or kind of work with multiple predictions at the same time for your complex decision. For example, for inventory management, you want to find, one of the inventory management just means how many, items to stock of different types. Okay, let's say you're a retail manager, you want to, you're selling a bunch of things and a bunch of products. You want to just figure out how many to stock, which means that if you prefer stocking one item for 100 units of such item and you only have 10, then you have to make purchase decisions for 90 more, right? So there is some decision you need to make. But how does it become complex is that every item may have its own demand function, which means you're forecasting what would be how many items will be sold tomorrow, how many items will be sold day after tomorrow, based on contextual factors, seasonal factors, and many other things, advertising factors, and so on. But every product will have its own forecast of how many sales will happen. But you have a limited budget or limited shelf space or whatever. So all these forecasts get intertwined in a let's say an optimization problem, and then you decide how much to stock of product one and how much to stock product two. So it's not a simple direct transformation of, hey, if the product's demand tomorrow is 10 units, today I should just order 10 more units. No, it's not per product. Each product's predictions goes into some sort of a black box optimization problem, and then you figure out how much inventory to keep for each product. And so it's not a simple mapping per product. Okay, from going from prediction to decision. In general, these types of problems, actually, there's a bigger class of problems called resource allocation problems, which not just in management of inventories, but allocation of resources like hospital beds to patients, or even like loans, right? So the person who's lender will have a budget of money, and they can't give loan to everybody, even if they are all approved. Right? Or if you are an investor in the stock market, even if you have a budget of $1 million, it's not like you can invest. Even with that constraint, you may want to have some less correlation between the things that you invest and things like that. So there is a generally for resource allocation, your forecasts become mixed with each other when you make decisions. So that's what I wanted to say with this slide, that sometimes decisions are complex. Okay. And there are some other names here, routing problems, like mapping trucks to things that you want to move from point A to point B and so on. But that's one complexity. And the previous slide about complex decisions had nothing to do with forecasting or nothing to do with predictions. Okay, in the sense that even if your prediction models are simple regression models, still there is complexity in decision making, right? There is nothing, you're not skipping over that. But in what we'll do for the next few lectures is really look at one type of decision making, which, as the lecture goal suggests, it's about online learning and online decision making. Okay, and the name in the literature, it's called reinforcement learning. And this is a slide, or this is a snapshot from several years ago, where one of the, I guess, magazines in the tech industry, they had a list of, and they keep coming out with these lists every year, just like Forbes list and so on. But among the list, one of the elements was reinforcement learning. Okay, this is just to give you a sense of, like, it's something that is not supervised learning, because many problems would be supervised learning, and then some problems would be unsupervised learning, which is what we've covered. But there are some small set of problems which kind of blur the gap between learning and decision making. And one of the problems area is called reinforcement learning. Okay. And that's what is a focus of study, not the complex decisions that we saw in the previous slide. So why reinforcement learning? It's because 10 years ago, 10, 11 years ago, some researchers from DeepMind, they showed a reinforcement learner. Okay, so this reinforcement learner, or some piece of software which has some learning behind the scenes, the software is making decisions just like a human, and it's playing games. Okay, in games you have to make decisions, whether to go left or right, or what move you want to make. And so they build this reinforcement learner, or some software, decision-making software, which would learn from its own experiences of playing the game, and learn what actions to take, what decisions to make at any given point of time. Okay, and this is a snapshot of the Atari collection of Atari games. These are 1980s, late 1980s games, 2D games. So, for example, this is called Breakout, where you kind of balance a ball which goes up and down, and the ball hits these bricks and they kind of vanish, and so you kind of clear those bricks. Okay, maybe in the break I can show an animation of it. So that was 10 years ago that this reinforcement learning based ideas kind of started becoming good. In fact, it's not that they showed that an RL type of a learner, a software plays these games well, but actually for a good majority of these games, it beats human players. Okay? That was a big delta in 2012, because anybody can write a kind of some software to play a game by controlling the inputs like the joystick. But it has to kind of do well, right? So that means that it cannot be just rule-based. It has to learn from its experiences, because it's not like a game like chess or something where rules are predefined, and given the rules you can make a move. Although chess has its own set of complexities, we'll talk about it later. And the second, actually related to chess, is the second big thing that happened a few years ago, again 6-7 years ago, which is again the same company was able to defeat in a 5-game setting the then #1 player in this game called Go. This is a board game. Rules are predefined. So you may say, okay, what is there to learn? I mean, if the rules are predefined, the software should just honor the rules and play. But to the state space, as in like the number of moves that each player can make here is too many. Okay, so you can't really figure out what is the best set of moves to make to win a priori. Okay, so you can only kind of partially solve this, and in the sense that this game you cannot just offline solve it and figure out what is the best thing to do in every situation. Okay, very similar to chess, although chess also has a similar situation in the sense that you know the rules, but you can't offline figure out all the possible things that you could do to win the game. So anyway, so there's another situation where the software that was built to play against the human player, where playing means putting these black and white stones on the board, and victory means covering, I guess, what is called more territory and so on. That software learned through previous games that humans played, as well as the software learned to play against itself, and that learning process involved reinforcement. Okay, and the word reinforcement here and in the previous slide and so on is all about trial and error decision making. You make some decisions, which is in this case moves, this case and the previous slide. You make moves, make decisions. You get a reinforcement signal, as in some sort of trial and error signal of how well you did, and based on that, you improve your model of what would be a good decision to make. Okay? So anyway, those were just teasers of where you could go. But today, as I said, we'll look at simpler instances of this type of decision-making problem. And this category is called online machine learning. Okay, and so first we want to kind of separate out from why is it different from supervised machine learning. Okay? And we'll do that not just today, but we'll do it next time also. This distinction between supervised learning and this online learning. Okay? So and then actually we'll look at something that is not exactly related to online learning called A/B testing also. Okay, it's a simple idea, and we'll not get into too many details, but it's worth looking into because that's actually a big part of real world data science. So what is online machine learning? It's basically this for loop here. Okay, so what you do, what is the situation is that you get to observe the state of the world. It just means that you get a feature vector. Okay, here let's call it context. You get a feature vector, you take an action. Okay, so this action can be your prediction of a forecast, or this action can be literally saying, do X, do Y, move, take a move, take a left turn, take a right turn in the self-driving setting, whatever it is. And then you obtain feedback on the chosen action. Okay, so you did a move and somebody tells you, hey, this move was bad, or you actually make a move. Let's say you took a left turn and hit a wall in your self-driving car, then you get feedback, right? Your car completely stopped. Okay, so you obtain feedback on the chosen action, and so this happens again and again and again. So what is the learning part of it is that hopefully you get to choose better and better actions. Okay, you choose good actions. Okay, in terms of some performance measure. That's what you need to learn, how to take good actions. Okay, and to take better and better actions, you have to incorporate feedback, right? So this feedback that you're getting, you have to incorporate in while deciding what action to take. Okay, so you can think of this for loop as a discrete time thing where you take an action, you get some feedback, use that feedback to maybe take a better action in the next situation. Situation, I just mean next time you get a feature vector and so on. Okay, so you can imagine after, let's say, 100 times of this for loop running, you would have 100 contexts, because 100 times you might have seen context, and 100 times you might have taken action. So it looks like you may have a feature label pair, right? Because there's a context and there's an action that you took. Okay, so it looks like a supervised learning problem. So where you can just say, okay, I just need to learn how to map from context to actions, but unfortunately that doesn't work. Okay, why is that? Is because the actions that you took, so what you care about is taking the best action in every context. Okay, what's the best thing to do? Because you hopefully care about achieving some goal, some goal like making a lot of money on the stock market and so on. Yeah, this is reinforcement learning as well. Yeah, online machine learning, online learning is reinforcement learning, same thing. But we'll look at reinforcement learning. Will kind of introduce the problem next time. So online learning is just this. Okay, I mean reinforcement learning is also a variant of online learning. Yeah, online just means you are kind of you're improving over time or over these indices. Okay, during this for loop you are kind of incorporating feedback and improving yourself. Yeah, so it is RL is also like this, but we'll not talk about RL because we've not even introduced it yet. Any other question? I was actually in the middle of saying why this is not enough is because you care about every context, you care about taking the best action. Okay, but if you think of doing this 100 iterations, up to that 100 iterations, what is the guarantee that the actions that you took there are actually the best actions? Okay, there is no guarantee, right? So in that sense, even if you learn a model, let's say with this 100 context and action pair, let's say it looks like a supervised learning data, even if you figure out the mapping, you're only predicting potentially a suboptimal action under those contexts. And even if it's generalizable, you may be under new context, you may be predicting something which may not be the best action. So there is this issue of like you can't really map it to a supervised learning setting, and that really depends on this feedback. So this is the second aspect of it, right? So why did we not take the best action in these previous contexts? And through feedback, can I just say that instead of saying that my label is my action that I took, I can say based on the feedback I should have taken this is the best action, and so now I have a clean data of context and best action, so I can just learn a function which maps from context to best actions, and any new context I can say what is the best action to take and be done, right? The problem is this feedback generally is not going to be that high quality feedback which tells you what is the best action. Okay, If the feedback was, hey, you did a bad action or whatever suboptimal action, and here's the best action, then you can log it as this context, this is the best action, and so on. Then the problem will be nicely in supervised learning setting. But we don't, the feedback is generally weaker than that. It doesn't tell you what the best action is. Okay, and that's because the feedback doesn't tell you what the best action is. That type of feedback is called bandit feedback, and we'll kind of come back to this word bandit feedback in a few more slides. But this at this slide, I'm spending a lot of time on this slide is because you just want to kind of remember that this is the for loop, and if you see this type of for loop, this is just called online learning. Okay, and there's both on the theory of machine learning as well as practice of machine learning. A lot of people have kind of used this as a template and discuss a lot of things about how things work and how things fare and so on. Okay. So, in this for loop, I'm taking actions. As I said, like this seems open-ended, like what actions to take, and I kept using the word best actions. And we can, the word best means that there has to be some measure of saying, the action that we took is suboptimal or not. The only signal that we're getting about actions is through feedback. So you can think of, in some sense, think of feedback as some number that you're getting. And so if you had taken a different action, you would have gotten a potentially different number, maybe higher number. And so that's what you want to optimize for. So actions that lead to higher numbers. And these feedback are basically numbers. And this feedback is also called reward. And you want to maximize this reward. Okay. That's what you want to do. And this is all qualitative at this point, and we'll make it concrete slowly over this lecture. Okay. And one assumption we're going to make for today's lecture, and this is not going to be true for reinforcement learning that he mentioned, is that my actions do not influence future contexts. Okay. This is a very, very important assumption, is that, for example, I'm an investor in the stock market, right? So-called day trader. If I buy 100 units of IBM stock or Tesla stock or something, it's not going to influence what the Tesla stock price is going to be tomorrow, because I'm such a small player, for example. And we'll see another example actually in this slide. I'll come back to that assumption in a second. But let's look at a more realistic example. I just, the finance example is one thing. So here's a situation where this is just a front page of some sort of news aggregator, I guess, MSN.com. And what is the ML problem here, or generally the machine learning problem, is to obviously show things that are actually interesting to people so that they stick around or click on things and so on. Okay, that's the general problem. The learning problem is obviously, I would like to show things which are most appropriate to these users. And so how do we map it back to this loop? Okay, we can always at this level we can say we can actually just not even think of the online machine learning paradigm and just say, okay, I can just solve the supervised learning problem, which is here are the user profiles. What did users browse before? Given that browsing information, what is the thing that I need to show? You can actually build just a supervised learning problem right there. Okay, but what we want to do is try to map it to online learning, which is that users arrive at the website with some information that is the context, and the vendor, the platform chooses something to show. Okay, that's its actions. Okay, actions now, as you can see, is pretty complicated. It's not just some discrete 4 or 5 actions, but something complex. And then user responds with some events, right? So click event, navigation events, and so on. Okay, and what you want to do is this choosing of content, news articles to show. Maybe there are lots of news events happening, but of which maybe some of them are relevant, or maybe the user only prefers music-related things, so you want to show music-related articles, whatever it is, right? So you want to choose content to yield desired user behavior. Okay? And the assumption that I mentioned in the last slide, specialized to this application, is that, or 2 slides ago, is that recommendations to one user do not affect other users, as well as the same user tomorrow, next time. Okay, which is a hard assumption, right? So if somebody visits this website like at 10 a.m. and 10:30 a.m., maybe their mood is the same. So there is actually this correlation, right? So in the sense that maybe you recommended bad recommendations at 10 a.m., maybe that influences how they perceive your recommendations at 10:30, okay, or whenever they visit next. So okay, that's the assumption being made. Now you can say, okay, why can't we just model this as supervised learning. Okay. The gap, as I said, is that we don't know what is the best action to take for each arriving context. Okay. Like in the realistic setting, for let's say the user arrived and I did take some action. I just showed some articles. Okay. And that becomes my data later to potentially train a supervised learning model. And it's exact same problem as before, right? So my data set therefore cannot be just the user profile and what I showed, because what I showed need not be the best thing that I would like to show, right? So there is this, you can't just use supervised learning is I guess the conclusion there, because if you want to map it as a supervised learning problem, you need to have labels or something. Maybe the decisions themselves you want to be saying labels. You want to have better labels than what the actual actions you're taking. Okay. Is the kind of distinction clear, or I don't know? Yeah.
I mean, kind of, but not really. Like, why can't you use the label as in what they clicked on?
Yeah, because what they clicked on depends on what action I took, which is what articles I showed. But what would have happened if I showed a different set of articles? Maybe there would have been more clicks. I don't know. Okay. Ideally, if I want to map it as a supervised learning problem, for every profile, I want to show things which hopefully yield the best. I'm not trying to. So if I just map it as a supervised learning problem, I am just learning what I would anyway do. Okay. In each situation, it just tell me what I would do. Right? That's not what I want to learn. What I want to learn is in each situation, what is the best thing to show so that I can actually make money, or whatever is the objective here, right? So, and this boils down to this feedback. Okay, this feedback is not telling you, step 3 is not telling you, hey, you chose these news articles. That's not good. If you had shown this other set of news articles, that would give you the most whatever desired behavior. Okay, this feedback is not saying that. It's only saying, what did you show? How good is it? How good is that what you showed? Okay. That type of feedback is very different from supervised learning feedback. So think of a situation where the input is an image and you want to classify it as a cat or a dog. Okay, and let's say it's an online learning group where you get an image, you classify it as a dog. Okay, and then you get a feedback, hey, it's not a dog. Okay, that feedback is actually pretty high quality feedback. Okay, when it says it's not a dog, you know that it's actually a cat. So in your training data, you can just go back and say, for this input image, the label is a cat. But here, if I give you just hey, how good is the news articles that you showed, you don't know what's the best set of news articles to show for this profile. Okay, or what is the right news articles to show for this profile. So there is this gap between the quality of information or the level of information you're getting. Okay, the technical term is called, this information is called, I guess, bandit feedback, and it is in contrast to what is called full information feedback. Okay. So supervised learning needs full information feedback, whereas with bandit feedback, there is an extra issue of, okay, what is the best thing to actually do for each profile? We don't know a priori. One thing you could do, get around this issue is that, let's say the same user comes 100 times. Okay, for the same user, you can show all the different things that you could show. Maybe there are only 100 different things you could show. Then you know that for each time they came, and let's assume there is no stochasticity in terms of how they respond to what we show. Then for every time the same person comes 100 times, we show all the different things that we have shown. Then we know which one is the best action to take, because among 100 different things that we showed, then 100 different actions that we took for the same situation, one of them is a better one, and we will learn what the best one is. And then we can, and now you can layer it off, saying, okay, take that observation as your supervised learning example, and then collect such information, and then you can learn a supervised learning model if you want. Okay. Yeah. Any questions now? Yeah. MSN, this website? Yes, I mean, a lot of these websites do in 2023. Yeah, a lot of them do real-time predictions. Yes. Yeah, MSN is a property by Microsoft. It's just like Yahoo or one of these websites. No, the first time it's not user. I mean, the version I'm mentioning is just first time you visit the website, just based on cookie information, and if you had an account or something with them, they would know what you liked and so on. Like say you are a music person or a sports person, or something, and they would like to show things which let you, which maximize those clicks or whatever they are. Right. So it's not adaptive in the sense of during your session, it's not going to be changed. It might change if you refresh and stuff, but this example is from a research project actually. So I don't know, and this is from 6 years ago or something. So I don't know what the current situation is. Yeah. Yeah. So this is just a pictorial view of what we saw in the previous slide. User comes with some information. You currently have a bunch of articles that you could show, but you can, and then given this information, there's a box which tells you what to show now. Okay. If it is supervised learning setting, it will say, okay, for this user, given these articles, what's the best thing to show now? And that would be good in supervised learning setting. But we don't know what's the best thing to show to this person. Okay? So this box will, show something and collect the feedback and improve, so that hopefully over time we actually figure out what's the best thing to show to this person. Okay. One way to improve is to, as I said, if the person comes again and again like 100 times, then you can literally show all the 100 different options and then figure out what's the best thing to show. But we want to be faster than that. Okay. Faster as in like number of interactions we want to kind of minimize. Yeah, so just to, if you ignore the details, the technical details of this online machine learning, what they did is, at that point of time, they have like 10+ million users, lots of requests per second, and with this online machine learning is a little bit different from supervised learning, right? It's not just, it's not going to be just prediction from given input. Here's the prediction and just move on. So there's a little bit of overhead in terms of compute, but they were updating. The underlying the green box that I showed in the previous slide at 5 minutes interval. We'll open the green box in eventually, so don't worry about it right now. And they saw, because of this, figuring out what's the best thing to show to each user, adaptively improving over time, they were able to show like increase in click rates in a particular test period. Okay. Just to give a sense of a realistic example, the realistic example has too many details and we don't want to get into the details. But there are many other situations. Doesn't have to be, here I'm mostly talking about marketing, but the same ideas have been applied to like mental health apps or any other like situation where you need adaptability, some personalization aspect. And that's not the only application. Also, there could be other situations where you need to go through that loop, and you'll see that box actually will have some source of randomness. Okay, this because it needs to figure out what's the best action to show, and so there will be some die throwing or basically some source of randomness in that step. Okay, to what to show. Okay, so if there are any questions about this. So this part was just trying to motivate, like, okay, there could be some complexities in real problems. What we'll do is, again, go back to basics and start with something that we are familiar with, at least from previous sessions, previous, I guess, courses, if you have seen it. It's called A/B testing. And then slowly build our ideas towards this issue of bandit feedback. And reinforcement learning also has this issue. Okay, you do trial and error. The whole point of trial and error is because you don't know what you get a feedback. You try something, you get some reward, and you don't know what would have happened if you did something else. And that's the idea. That's the issue with the feedback. So what are we going to do? We're going to look at A/B testing and then slowly talk about the loop again and again. But what we'll do in these 2 bullet points is that we actually even going to get rid of the context. Okay, even if we don't know, even if the same user coming in again and again, as I said, the problem is if you have 100 actions to take, 100 different actions to take, do you show each one after the other like 100 times, each action once, for example, and then figure out, okay, one of them is giving me the most feedback, and so that's the best one, right? That's really the base case. But that doesn't work the moment you have randomness. Like, what if the reward, or what if the user with some probability likes the articles that you show. With some probability, they'll, even if they may not like it. So if there's stochasticity, even if you have 100 actions, 100 rounds are not enough. You may need 200 rounds, because if you do 200 rounds, you'll get 2 samples per action. If you do 2000 rounds, maybe you'll get 20 observations per sample. Then you can at least get rid of the stochasticity. Okay, so that's the mental framework we need to have here. Okay, how to be efficient while figuring out what the best action is, even when there is no change in the context, even if it's the same user or same thing happening, same situation happening again and again. Okay, so let's look at this from the perspective of A/B testing. Although, because A/B testing is basically randomized control trial, A/B testing, what is called a split hypothesis test, I guess. There are different names to this, I guess, technique or mechanism. And it's a nice intersection of statistics and decision making, because A/B tests are all about making a decision based on data where you actually run a so-called experiment. Okay, so I mean, and what is the scenario? And by the way, this A/B testing is a huge part of industrial data science. So many of you who are planning to go into industry, you might end up, with a decent chance in a team which does the A/B testing, especially if it's marketing or especially in the, I guess, the tech area. Okay, so if there are multiple competing ideas and you want to make a decision after making some field observations, just means that you want to make decisions based on building out those ideas and then actually exposing it to users and getting a sense of which one actually works. Then you use A/B testing. Okay, so it's just a 2-sample hypothesis test. That the statistics part of it is well understood if you don't fall into any of the pitfalls related to hypothesis testing, which is peaking and all those things, p-value hacking and all that. But the value of such a mechanism, this A/B testing tool, is actually immense, right? So there are actually billion-dollar companies today which provide these services for large enterprises, and even for small companies, there are a lot of startups in this area. And all the big firms that you have heard of, Google, Facebook, Amazon, all of these guys do A/B testing, okay, for everything. And non-tech industry also does A/B testing, which is randomized controlled trials. Makes sense for clinical trials for sure. And they may be a little bit controversial for social science experiments, but people have done that as well. Okay? So basically, we want to figure out, we have 2 situations and we don't know how well 2 situations, 2 ideas, or 2 versions of 2 decisions that you need to take. One decision you want to make, which is whether to pick this website as your homepage or that website as your payment page. Okay, so you don't know a priori, and so how do you decide which one you want to end up with? And the only difference between these 2 is there's an extra coupon code field in the second one. Okay? So what do you guys guess? Which page has a higher conversion rate? It just means that people actually proceed to check out and pay you money for the service. Which one do you think is? If you have not seen the slides, first one has a higher conversion rate. What anybody who's saying second one? No. Why not the second one? I guess let's. Yeah.
The moment I see a coupon code, I change my browser and try to find a code. If I don't find one, I don't end up finding it.
Yes, that's true. So I mean, this is a very toy example, but yeah, with B, you lose revenue. So you just want to find the coupons, right? So sure, I mean, this is a simple toy example. You may know what the user behavior could be, but when you make some other types of changes, like going from a recommendation algorithm 1 to recommendation algorithm 2, okay, like one is based on matrix factorization, the other one is based on neural networks. We may have offline numbers, offline precision recall or whatever those metrics are for recommendation systems, but we don't know how users are going to behave, right? So how does YouTube get to choose its whatever video recommendation stuff, things that it shows? they have teams which build different competing solutions. Maybe offline they can measure something, but at some point they have to hit the road, as in actually expose to real users and get a sense of which one works, right? So so A/B testing is a good situation where we can ignore the not just the contextual aspect of our online machine learning problem, but also the online aspect of our online machine learning problem. So what do I mean, right? First of all, there's no context. Okay, let's say there are two products, like two settings. One is control, one is treatment. Okay, there is no we don't care about context, and also there is no online aspect, in the sense that our action our action should be to expose website 1 or website 2 in the previous example, right? We're not even going to try to adapt and improve our action over interactions. Okay, we'll just we don't want to online learn. We don't want to learn anything in the online part. After doing the A/B test, we will collect data for option 1 and option 2, control and treatment, and then figure out whether treatment is better than control or what the other direction. Okay, so we'll figure out the best decision, but in the offline, after the interactions are already done. Okay, so we'll ignore the instantaneous feedback, in the sense that we'll collect the feedback, but we'll not use the feedback to improve our action in the next interaction. Okay, so that's what A/B testing is, right? We're not gonna we're gonna pre-decide here's treatment and here's control, or here are the two options. And the whole part of randomized control trial is to randomly assign incoming users to one of these two options, the treatment and the control, and the number of interactions that each control or treatment is part of is pre-decided also. Okay, so there are some choices you need to make, like, oh, if we believe that the treatment is better than control by X%, maybe that determines the the sample size that needs to see each of the options, and then you pre-decide the sample size, and then you let those many users interact with each of the options, and then collect data, and then you actually do the A/B test, actually do the statistical test. Okay, so there's nothing, you are getting feedback of, obviously you're logging the feedback of whether product A is better than product B, but you're not taking that into account while deciding what needs to be shown to the next user. Okay, next user, with 50% chance will see option 1, or with 50% chance will see option 2. And not just for A/B, this extends, all our discussion extends to A, B, C, or whatever, multiple hypotheses, multiple situations, multiple treatments. So this is summarized. Users come, let's say in the two option setting, users basically diverting 50% of the users to one or the other, and you're just logging the information, and then you're doing an analysis, which basically is like a two sample hypothesis test. Okay, and your whole idea is that the only difference between users or these two situations is is what you're exposing them to. Okay, in the sense that on average the user seeing this is the same as the user seeing that, and since there's only one difference, which is the option 1 versus option 2, that means that this option is the reason for a difference in some outcome. Okay, and nothing else about the users is relevant. Okay, even if the users are all sorts of users, maybe students and working professionals and all that, all those covariates don't matter if you're randomly assigning users to these options. Okay. Yeah, I mean this slide is just talking about this random assignment being an important thing. It eliminates biases and confounding, or basically correlating users' actions with their covariates. Okay, maybe younger students kind of prefer one type of option versus working professionals or something else. That type of correlations is completely removed because people are randomly being assigned to one or the other. Okay. So that's the part where you make the users see these options and log what they do. But once you log what they do, in the sense of did they interact, did they check out, did they do the necessary action, then you are basically asking whether the true effect, okay, let's call it mean effect, let's call it mu1 and mu2, maybe the mean number of clicks, for example, if you show the MSN type of a website, whether that mean value is different from one option versus the other. Okay, and if it's different, under what assumptions, you can quantify that. And there are many different. I mean, this is just a recap, just connection to some hypothesis testing that some of you might have seen in 570 or some other course. But basically, there are different ways to kind of set up your hypothesis test. Okay, once you've collected the data, right? So there are different viewpoints, I guess. One of them is a Fisher viewpoint, where you kind of reject the null hypothesis, or not, or you don't have enough evidence to reject the null. Okay, so that's one viewpoint. And the second one is Neyman Pearson, which is you look at what's the likelihood ratio, what is the probability of data under the null, or what's the probability of the data under the alternative, and then you can choose one or the other. And the Bayes inversion of doing this is where you also include the priors of what's the likelihood of the null, or what's the likelihood of the alternative. Okay, so I don't, this is a bit tangential to us, but what we want to capture is that we have this online learning group where we said, okay, let's ignore the context for a second, which means that we only care about whether decision 1 is better than decision 2. Okay, by effectively exposing the same thing to essentially the same user multiple times, which is what we did in A/B testing. And the second thing we also ignored is that we're not taking the feedback into account in the interactions. Like, we're not being dynamic. We're just we're taking arbitrary actions, essentially random actions through the interaction, and then after the interactions ends, we figure out which one is the better action, which is not very effective, because your goal during those interactions is to take better and better actions so that we actually maximize our feedback or reward or whatever. Okay, so any questions about this, about A/B testing? Although we did not discuss it, it was only a 5-10 minute treatment. It is actually the big part of data science and industry. As I said, it's most used in the industry compared to what we'll see next. But what we'll see next gives you fundamental ideas about what is the trade-offs happening in this decision-making, learning plus decision-making, simplest learning plus decision-making setting. Okay. Okay, so there's a lot more to discuss about A/B testing, but I will skip a couple of these slides. But what's the connection to the next topic, which is multi-arm bandits, is that what if we can change who sees what, as in which user sees what treatment dynamically, in the sense that if you recall, in A/B testing, you need to decide sample size beforehand, in the sense that there's an option, there's a control and a treatment. You probably decide, okay, 1,000 users should see the control, 1,000 users should see treatment. Okay, that's where the 1,000 number come from. Maybe your minimum detectable effect size is something. You plug into a formula based on your test, and that will tell you what is the sample size you need to have per arm, per treatment. Okay, so you pre-decide that. But then what happens if maybe in the first 20 interactions on each side, you get a sense that maybe option 1 is so bad that it's very different from option 2. Okay, that means at least in A/B tests, you're not allowed to now suddenly stop that experiment there and conclude that option 2 is better than option 1. Okay, that would be called, I guess, peaking, or like adaptively stopping the experiment. That's not valid, at least in the simplest settings. You might have to take into account while doing the statistics later. But what if you could do it dynamically, in the sense that as you observe that maybe option 2 is better in the first 20 interactions and option 1 seems to be lagging, maybe in the 41st interaction, after 20 and 20, in the 41st interaction, you prefer option 2 a little bit more than option 1 while showing it to the next user. Okay, so you're preferring the better option more and more as you are having more and more interactions. This is dynamic. Okay, of course, we don't, after doing this, after showing option 1 and option 2 are the two decisions of which action to show, as in which website to show is your action. As you're doing it dynamically, the data you're collecting may not be useful for the hypothesis testing anymore. But by being dynamic, you are able to maximize your goal, because your goal was to actually maximize the reward collected. Okay, maybe option 2 is leading to more conversions. By the end of those 2,000 interactions or whatever, you want to have more conversions. Okay, that's so it's a different goal, and so being dynamic is actually useful. Okay, and not just that, and we want to also include context, and that's called a contextual bandit setting. So it's a little bit more complex. So let's first talk about multi-arm bandit setting, and then introduce context into the picture. Okay, so what we've done is a brief recap of A/B testing, really qualitative, not too deep. But if you go back to the online machine learning loop, we don't have context. So if you don't have context, it's as good as saying, okay, if we have 10 actions or 100 actions, we just need to figure out which action is the best. Okay, and so we're having all these interactions. One dumb way to do it is, okay, show the first action once, and then in a round robin fashion, take the second action next, and next interaction, take the third action, next interaction, so on. Right? You could do that in the round robin way. And you could, if there's randomness, you could do it again and again and again a few times, so that you get good estimates for each action, and you can figure out what the best action is. Okay, and that's essentially effectively what we're doing with A/B testing. We're not being adaptive. Even with round robin, we're not being adaptive. So what we want to do is be efficient. Okay, because we want to be more efficient in the sense that we want to, if something looks promising, some action looks promising, we want to take it more, so that we actually collect rewards for that action more and more, because maybe potentially that action is better, so that in that overall interaction period, we're actually able to do well. Okay, so that's the goal. So which regime does this make sense? Is that when you want to be more data efficient than just A/B testing. Okay, so contexts are still not there. So let's get into Bandit settings. And this is just, okay, so the way all this proceeds is with A/B test also, there's a problem and then there's a solution technique. Okay, and the problem is we wanted to figure out which action is the best. Okay, and we were not allowed to dynamically adapt, action 1 versus action 2 to show. And given those constraints, A/B test was a way to go. Here, the problem is still the same. You want to kind of problem is the same as the online machine learning goal, which is to collect as much reward as possible. Okay? And these 3 figures here correspond to 3 potential actions you can take. Okay? Just an example illustration. And in each interaction, you get to choose one of these slot machines, or not slot machines, like these machines to play with. Okay, and if you pull the arm, pull the arm basically is equivalent to saying take that action or make that decision. You get some reward, right? This is a very literally, if you pull that machine, you get some sequence here, and based on that, you might get some reward, right? And what you want to do is, as you interact more and more with this, by taking these actions, there's no context. Okay, every interaction you get to pull an arm or play one of these machines. You get some reward, and what you want to do over these interactions is to adapt towards the machine which is actually giving you more reward. Okay, you want to kind of converge towards that machine is actually giving you most reward, ideally, right? So these machines are stochastic, right? So it's not like every time you pull these arms, you get the same reward, right? So there's randomness. So that means that there may be a mean value for each one of them. Maybe the mean reward for this person is 0.1, maybe, which means that 1 out of 10 times you get $1. Maybe here, 1 out of 20 times you may get $1, and here 1 out of 5 times you might get $1. If you know that numbers already, you would obviously go with this. Okay, 1 out of 5 times you're getting $1 is like the best thing, but a priori you might not know, right? So this is where either you could do just round robin, try each one, try the first one 100 times, try the second one 100 times, try the third one 100 times. Okay, so then you can estimate, some estimated mean rewards, and then you can see, okay, maybe the estimated mean rewards are close to true rewards, and so I figured out that maybe the last one is the best one. Okay? But that's not efficient. Okay, you want to be dynamically after every interaction figuring out which one is the best, and hopefully you kind of converge towards the best and play that more, so that over that 300 round interaction you collect as much dollar as possible. Okay, that's the objective of this setup. Okay, any questions here? I am going to introduce a little bit of notation, but it's not heavy. So we'll have capital K arms, so like 3 arms in the previous figure. 3 arms correspond to 3 actions or 3 decisions you can take. Okay, each corresponding to an unknown distribution. Let's say the distribution is Bernoulli, like with some probability it will give a reward, with some probability it will not. And each time the agent, as in we, the person who wants to learn and dynamically figure out, pick these actions, pulls one of the arms among these 3, 1 to K or 1 to 3, and then we observe a reward. Okay, if it's Bernoulli, it's 0 or 1, right, with some bias. And so we get a reward, and the objective is to maximize the expected sum of rewards. Okay, now we are trying to make it more concrete. Our objective is, let's say we get to do this, these 2 things at each time t. So maybe we get to do this 300 times. Okay, 300 interactions. Okay, 300 iterations. The objective is to maximize the expected sum of rewards collected over those 300 interactions. Okay, so if I already know that the third one was the best, I'll always keep trying the third one. So out of 300 interactions, that's the best I can do. Okay, in expectation, right? So this. So that's the benchmark. Okay, so if you knew everything, you would get, what the mean reward for each arm is, each of the 3 arms is, and then the best guy would be mu star. Okay, let's call it max over these mean rewards. And so this is the best arm, a mean reward of the best arm, and this is what you want to kind of get towards. Okay, on average. So what we did in the previous slide is, on this slide, we're going to just set the problem. Okay, so in the previous slide also we just said, okay, these are the mean rewards, and if we knew the data, then one of these arms would have highest mean reward. Okay, even in this slide, we're going to set the problem, finish setting up the problem, as in we'll finish setting up the objective of this problem, so that once we set the objective, then we can talk about solutions. But even before that, we can actually talk about a couple of solutions. The round-robin solution that I've been talking about, or just picking a random arm or always playing it, are terrible ideas, right? If you pick the same thing, same arm again and again, a priori, like out of the 3 things, you just pick the first one and you play it again and again and again, then you are not, you're not going to improve, because you're getting feedback, but you're not using the feedback to figure out whether second arm or third arm could have been better choice, right? Round robin, you predetermine that you're gonna do the first arm once, second arm once, third arm once, and again go back to first arm once, second arm once, third arm once, and so on. So you're just looping through the 3 options, right? You're not again being adaptive. So these strategies are not good. So actually we want to be better than these strategies. Better in terms of what? Better in terms of collecting these sum of rewards, okay? And how do we evaluate it? Let's say there's a little number of rounds. Okay, so maybe those 300 rounds I was talking about. Maybe there's 300 rounds. In those 300 rounds, if you knew which arm is the best one, then on average, this is the reward that you get by trying that arm. Okay? This is the expected reward you can get if you know which arm is the best one. If you try that, this is the expected reward you can get. Right? N times that is the sum of the rewards that you can get, because every round you'll try the same thing. So n times the mean reward, mean of best mean reward is that. And what you actually do, because you don't know which one is the best one, is try different things. Okay, in round 1, you'll try arm 1, maybe in round 2, you'll try arm 2, round 3, you'll try maybe again arm 1, maybe arm 1 seems promising. So here you get to be dynamic. Okay, you look at feedback that you're getting. You're collecting, like every time you try each of the arms, you're getting a sense of which one is, you're getting an immediate reward of trying that arm out, and therefore you're keeping a log of which one seems promising. Okay, as long as you can be adaptive, you'll collect this over the period of those 300 interactions. Okay, now the difference between these 2, okay, is going to be positive, because you can never beat this in expectation. Actually, let me not even talk about positive and stuff, because xt is the reward for the arm that you played at that time, at time t. Okay, this reward can be anything. Okay? It could be because it's stochastic, it could be, you don't need to get the mean reward only. You can, even if the mean reward for, let's say, an arm is or one of those machines is 0.3, you might get still 0 reward, because with 70% chance you might get 0, right? $0. So this difference is called cumulative regret. Okay. And the expectation of this, okay, expectation of this thing is what? So this is not a random thing at all. These things are random, but a sum of random variables, expectation and the sum kind of interchange. Okay, that's a key property with expectation, the linearity of expectation, right? So, and then once you put expectations here, you'll get some, depending on which arm you try, the mean of that arm would be part of this. Okay, so let's say mu1 plus mu3 plus mu2 and so on. Okay, whichever arms you try. Obviously, that sum is going to be smaller than this. Okay, in that sense, so the expected value of this is going to be positive. Okay, and that term capital R over the little n number of rounds is called cumulative regret. Okay, so the expected cumulative regret, which is written here, is what we want to minimize. Okay? We want to minimize this, and then whatever we do, we want to be collecting rewards as close to the best thing we could have done if we knew what the mean rewards were a priori. Okay, and so first of all, this whole objective has been set in terms of expectation. By the way, that's one thing that I'm not emphasizing, but we are talking best in terms of expectations. And second thing we're saying, do whatever you want. A priori, I want, we don't know which of the three bandits, which of the three actions is best. Do whatever you want, but whatever data, whatever rewards you collect, in expectation, hopefully they're not too far away from what's the thing you could have done if you knew the answer a priori. Okay, so this seems like a reasonable objective. Okay, so either you minimize the regret, or if you don't want this expression, you can say maximize the rewards of this. Minimizing the regret is the same as maximizing the second term, so it's the same idea. Okay, so now we'll come up with some ideas which do better than these guys. Okay, like for example, if you do round robin on those three arms, 1/3 of the time you're choosing something bad. Okay, sorry, 1/3 of the time you're choosing the best one, and 2/3 of the time you're choosing the suboptimal ones. Okay, so at least 1/3 of these terms get cancelled in 1/3 of the terms. So thankfully, those that don't contribute to regret, but 2/3 of these terms, they'll leave some money on the table effectively, right? So there'll be a regret for round robin for sure. Okay, so we want to be doing better than them. Okay? How can you do better than round robin or constant strategy or just randomly flipping a coin, and picking one of these arms at random? Is you have to take that feedback into account. Okay, which means that you're getting you try an action, you get a feedback. You try an action, you get a feedback. Based on the feedback, you kind of slowly, actively, start playing the arm which has higher mean reward, estimated mean reward, for example, while taking into account the statistical issue that your estimate may be off, and so maybe the other arm is better. Okay, so that's the trade-off here, even without context. So this way, you can be more sample efficient, okay, and collect more reward and therefore have lower cumulative regret. Is this clear? This is a very completely different thing from our supervised learning and unsupervised learning stuff that we've been seeing over the past several weeks. So it'll take some time to understand the issues here. Okay. The issue here is that, although we're getting into the details now, the bigger issue is that even without context, the feedback is a bandit feedback. Okay, let's just go back to the picture, right? So if I pull this arm, I get some dollar value, which is like a reward for pulling this arm or taking this action. I have no idea what would have happened if I played these two, right? So I'm only getting feedback on the thing that I tried. I don't know what would have happened if I did something else, because if that's different from pull information, where, for example, let's say these are the three class predictions you're making. If I say predicting, let's say, given an image of a cat, I say it's a dog. And if somebody tells you, oh, hey, it's not a dog, it's actually a cat, that's more information. That's not only saying that what you said is wrong, but also saying what is the right thing. Here, it's not happening. Okay, and this is a more realistic decision-making setting, actually, where unlike prediction settings where you would get, your label is wrong and this is the true label, here we are not getting that. Okay, so that's the bigger issue. And so even without the same context, so there is not even a model to learn because there's no input feature vector here. There's nothing to input. even when there's nothing to input, because of the bandit feedback, you have to kind of do some learning. Okay, there's a learning of what is the best action to make in that single feature setting. Okay, so it's as if we are in a canonical setting where there's only one feature vector and it's always the same. Even then, we don't know what's the best label to predict. Okay, that's the base case we are looking into. Okay. Okay, so let's look at a very intuitive idea. It's called the epsilon greedy approach. Okay, so now what we're getting into is solutions for us to minimize our cumulative regret. Okay, while basically what we're going to do is this. Okay, here's the algorithm. At each time period, so we will have a parameter epsilon. Okay, each time period, with this parameter, we'll use a coin. Remember, I showed a die when we showed like the MSN example, or around that time I said the algorithms have to have some randomness. So this is like randomness. The epsilon is like the bias of the coin. I'm going to flip that coin with probability, and the coin is going to land heads or tails. If it's heads, I'm going to take the subjectively best arm, as in based on my feedback log data. Or if it lands tails, I'm just going to pick an arm at random. That's what is being stated here. Here there's some words, and I'll tell those words in a second. But basically, again, what is the strategy? The strategy is every time I need to maintain a sense of what is a subjectively the best arm so far. How do I maintain that? Is because let's say I'm in the 50th interaction. By the 50th interaction, there was these 3 actions. I would have already maintained. I would have already probably tried the first action 10 times, the second action 20 times, the third action 20 times, for example. Okay. Which means that given those 20 trials, I would have a sense of what is the estimated mean for each of these 3 actions, right? So based on the estimated means, maybe the third one looks good. Then with some probability, I'm going to try the third one, okay? And with some other probability, I'm going to try something random, okay? So trying something random is called exploration, and trying your estimated best arm based on your previous feedback data is called exploitation. Okay? So there is this exploration trade-off that is needed to handle this bandit feedback issue. Okay, this is the big thing, and you'll see that this epsilon greedy or exploitation trade-off also comes in reinforcement learning a couple of lectures later, or next lecture, or a couple of lectures later. Okay, so all RL algorithms. Okay, I haven't even told you the problem setting, but all solutions will have some way to try something different. Okay, the trial and error has to be there. Okay, this is the trial and error aspect of this solution. All solution strategies. Round robin did not have this. Round robin just said try one, and then come back, try the first one again, and so on. Right. So any questions about this strategy? Okay. So the strategy is easy to state, but it actually leads to some very interesting situations. As in, as the interactions progress, the subjectively best arm might change. Okay, it can change, and obviously as you interact more and more, you're getting better and better estimates of various arms. Okay, but it's not uniform. Okay, it's adaptive because the subjectively best arm is getting potentially higher number of tries compared to all the other guys, all the other arms. Okay, but you do try the other arms once in a while, and maybe if they're really that good and they give higher return or higher reward in those rounds, then they might become subjectively best arms moving forward. So there is a chance. So what we're trying to do is like spend more time on things which are subjectively best. Okay, so based on our previous estimate, based on current round, whatever we have had the feedback log so far look the best, they might be preferred. Okay? So this picture here is just showing if I'm in the current time step C, 1 minus epsilon, try the best thing. With epsilon probability, you have to try something randomly, and since there are k arms, 3 arms for example, you have to try 1/3. So this epsilon probability times 1/3 probability, try the first arm, and so on. Okay. Yeah.
I think you talked about this, but at what point do you start using the strategy? Like after you exhaust?
Oh, it's from time period. Okay, so at what point you need to start the strategy is there is an initial cost, and you need to know what is the projected best arm. So you have to at least try each arm once. Yeah. So you may say, oh, if I'm already trying each arm once, at the end of the 3 trials, I would know what the best arm is. That's not true because of stochasticity. If there was no stochasticity, then yeah, then the problem is like simpler, right? So you just try each arm once and you know what the best arm is, and then done, right? And always keep playing that. Right? So I mean, the reason why there was this name scientist and businessman is because maybe scientists does exploration, whereas businessmen do exploitation, perhaps, of in terms of research versus like I guess product production. So here's an interesting figure. Okay, so that was the strategy, and by the way, that's not the only strategy. In the epsilon greedy strategy that we discussed, for example, you could even tune epsilon as a function of interactions. You can make epsilon bigger or smaller as a function of interactions. Okay, because maybe early on you want to have more exploration because you don't know which one is better, but later on you don't want to have too much exploration because you probably know which arm is actually better. So to control the exploration level, you can change epsilon as well. Okay, but let's not look at the more complex things. Let's look at this setting where there are 5 arms. Okay, so instead of the 3 arms that in our illustration, let's say there are 5 arms, and each arm has this mean reward. They are Bernoulli arms. Bernoulli just means that literally like the slot machine there, where 0.1 probably means 1 out of 10 times you'll get $1. Okay, that's it. And let's say the last arm has the highest probability of reward probability. Okay, which means that if you know this beforehand, you will always try the 5th arm all the time. Okay, to get the n times 0.9. If there are 300 interactions, 300 times 0.9, whatever is the number, is the total reward you can collect if you knew everything beforehand. Okay, but you don't know them don't know it beforehand. So what you're going to do is for some, and if you're going to choose epsilon greedy strategy, you have to choose some epsilon value, right? So let's say we choose epsilon is equal to something. It's a 0.5. Doesn't matter. It's epsilon is 0.5. It's a parameter of your approach. Then with epsilon probability, so as I said, you will do at least 1 round of interacting with each arm. So you'll get 5 numbers. And so at any given point of time, so x-axis represents time as in interactions. Okay, it's a discrete time. So in every interaction is like 1 increment in time index. And then the y-axis represents the probability of selecting the best arm. Okay, we know that the best arm is the 5th arm already. So using our strategy, it's just showing how does the probability of choosing the 5th arm change. Okay, so because of epsilon greedy strategy, early on, each arm is going to be chosen, essentially at random, uniformly at random. Like the probability of choosing the best arm, for example, is 1 out of 5, at the beginning. But slowly, you're going to start playing that arm more and more. Okay, so obviously, epsilon being high means that the probability of choosing the best arm kind of has a lower upper bound. Or just mean that it's not going to go, the probability of choosing the best arm doesn't go too high because you are forced to explore 50% of the time. So only the remaining 50% of the time you will play the best arm. So, but 50% time you're going to do random stuff, and 1 out of 5, the 50% of the time will be the best arm also. So you'll a little bit higher than 50%. So 55 or whatever, 50 or 60 or something. Okay, so it's just showing how by just using epsilon greedy, you are able to actually play the best arm as more and more interactions happen. This is dynamic. Okay, this is actually a key plot difference from, let's say, round robin or A/B testing. A/B testing, the probability of selecting the best arm, since there are 5 arms, is 0.2. Okay, in A/B testing or something which is not enough, or let's say round robin, it will be 0.2, because every fifth round you're going to pick that arm. So on average, it's just 0.2. So which means if you're going to be selecting the best arm lesser number of times, then you're going to be collecting less reward. Okay, the more with higher probability, if you're going to be picking the best arm, the higher the rewards you're going to get. Okay. Any questions about this? No questions? Bye. Okay, so let's look at one more algorithm, and then maybe we can take a break. The second solution approach, it's called upper confidence bound. Okay, these are all, by the way, in our in our treatment, we are going to just focus on intuition here. Obviously, there's going to be a lot of mathematical details that I'm gonna skip because they're not very important. Okay, it's not important at the first level. Maybe if you really get into the details of how this work and so on, there may be some mathematical details needed. But so let's look at the second approach. Okay, it's a epsilon greedy was flipping a coin and picking an action at random, or picking the most promising so far with with some probability. Okay? So upper confidence bound algorithm is just trying to smoothen it out by not flipping things, picking an action at random. Okay, how do we do that? Here's the approach. What we're going to maintain for each arm. So what we're going to do is, if we have 3 arms or 5 arms, for example, we're going to maintain a number for each arm. Okay, one scalar number for each arm. Remember, there's no context. We just need to figure out which arm is the best one and keep using that, hopefully, to collect most reward. So what is the number we're going to maintain? A part of that number is just the estimated mean reward so far. Okay? For example, the first arm, if I play 10 times and I got a reward once, then my estimated mean reward is like 0.1. So that's the number. And then maybe for the second arm, I play 20 times and I got 0.3 as 3 times reward and 0.3. Okay, 0.3 by 2 or whatever. Right? That's the first number. And then there's going to be another number that I'm going to add. It's we're just going to call it the bonus term, but basically, this is the term which is kind of related to this upper confidence word here. But basically, this is the term which is trying to say that if you have is a function of two numbers. Okay, t is the interaction round. So maybe if t is like 50th round, then 2 log 50. Okay, and t is 250th round and 2 log 250. So t is just the index of which round you're in. So that means that the numerator is slowly increasing. Okay, the denominator s is how many times have you played this arm so far? Okay, maybe arm 1 was played only 10 times. We are, let's say, we're in the 50th round, and arm 1 was played 10 times, and arm 2 was played 20 times. Okay, then s is going to be 10 for the first arm and 20 for the second arm. Okay, it's just a count of how many times you played that particular arm. Okay, it's not, although there have been so many interactions, in those many interactions I played different arms so many different times. Okay, how much did each arm? How much did that arm? How many times did that was that arm played? Sorry. Yeah. So this is a number. This overall sum is what you want to maintain per arm, and then your strategy. There's no source of randomness here. The strategy is to just take the arm with the highest maintained number. Okay? This number is just the same as this. Okay, where this corresponds to just the current. This just corresponds to how many times you played that arm so far. Okay? So anyway, so you have this number for each arm, and your strategy at any given point of time is to just play the arm with the highest this combined number, this number, and that's it. Okay. Now we'll try to understand why this makes sense. Okay. Any intuition? Nobody's looking at the screen or me. So remember what we're trying to do, right? So we just want to kind of explore and exploit. In greedy, it was clear. We're going to explore with some percentage, with some percent of the time, and exploit some other remaining percent of the time. In each round. Sorry, we're going to flip a coin with epsilon probability, and if it lands heads, we're going to explore. If it lands tails, we exploit. Here, what we're trying to do is maintain estimated rewards. So if this number is not there, and if these numbers were there, then there's no way to explore. Because if you're just going to make decisions based on mu hats, then let's say by the 10th round, the first arm has a higher mu hat, then you play that arm because of the strategy. We're just gonna the arm that we play is just the max of those numbers. And if the second term is not there, let's say by the 10th round, the first arm looks more, has the highest mu hat, then I'm gonna play that in the 11th round. And I'm gonna play that in the 12th round and so on. Unless in the 11th and 12th round, the numbers, I get flow numbers such that this mu hat becomes lower. Okay. So the exploration aspect is only comes up, like it's as if the second term is not there, we'll latch onto one of the arms until its mean rewards falls down, we're going to continue to play it. Okay. But what the second term is bringing is to bring that exploration aspect. It's saying that if an arm has not been played too many number of times so far, then this term is slowly, it's as the denominator will be small already, and log t will be growing. Okay, which means that this term is going to be higher than other guys. Okay, so especially for an arm that was only played like, let's say 2 times out of 100 interactions, the denominator will be 2, and so that this bonus term will be so high, the upper confidence term will be so high that now that arm has a, has a high combined value, and so that arm will be played in this current round. Okay, so basically the second term is just trying to ensure that you don't ignore the arms that were played too infrequently. Okay, so it's actually inducing this exploration. Okay, the upper confidence bound name for this heuristic or this heuristic comes from the fact that this sum is in some sense an upper bound on the true mean reward of this arm with some probability. Okay, so which we don't care about at least for this narrative. So that's where the word comes from. So this term should be an upper bound for the true reward with some high probability. Okay. So that's the UCB approach. So here's a different plot. Okay, unlike the epsilon greedy, here I'm showing you just our objective. Remember, our objective was to actually minimize cumulative regret or maximize the collection of rewards, right? So why not just look at that as a function of interaction? So on the x-axis of interactions, it's a huge number here, million interactions, and there are only 10 actions. Okay, 10 actions with million interactions. You would think like it should be very obvious how to figure out which arm is the best, right? And that's true. So in this case, even if you do round robin, you probably will be able to, do round robin for some amount of time and then just to figure out which one is the best and then play. That would also do well. And here, in this synthetic setup, 0.5 divided by k is the mean reward for each of the actions. Okay, so some slowly decreasing number. So first arm will have 0.5, second arm will have 0.5 by 2, third arm will have 0.5 by 3, and so on. Okay. There you can see that this UCB algorithm has this blue curve. This is the performance. Okay. Cumulative regret, remember, is first of all, since it's regret, we want it to be small. Right? Cumulative regret should be small. Since it's cumulative, it should it cannot go down. Okay, suddenly you can't make if you've played a suboptimal arm, there's no way to undo that. Okay. So this is actually an increasing, should be increasing function, but should not increase too much. Okay, as a function of interactions. And it turns out that the algorithm that we saw, the UCB algorithm, okay, it turns out that has it comes with a guarantee that the expected cumulative regret is upper bounded by log n. Okay? So forget about the C and K. C is just some constant. K is the number of arms. So let's say 3 or 5 for us, or 10 here. Basically, some theoreticians have proved that the previous algorithm with that formula, that combined number, and you're picking the arm with the highest number, its expected cumulative regret is actually upper bounded by log n, which just means that it grows slower than log n. Okay? So if this as a function of n is smaller than log n, means that remember log n is a function of n, it's an increasing function of n, but it's not like if n is equal to n, that's a 45-degree line. If y is equal to log n, it's a curving line like this. And they show that expected regret, cumulative regret, is smaller than that, grows smaller than that. Okay, and this type of a result is actually very important for learning. Okay, when does an algorithm not learn? Is when the expected cumulative regret as a function of n for that algorithm is actually linear in n. Okay, which means that it's actually true for round robin strategy. Okay, because in round robin, remember, if there were 3 arms, then 1/3 of the time I'll be obviously playing the best arm, but 2/3 of the time I'll be playing the suboptimal arms. Okay, which means that this regret will actually be order n. Okay, which means that the 2/3 number is never going to go down to 0. I'll always be 2/3 times being suboptimal. Okay, here, so that means that round robin there is no learning. I mean, that's clear because we're ignoring the feedback. Here, because we are maintaining estimates and we are trying to take into account exploration and exploitation, it turns out that you can actually do better than you can do better than being n. Okay, so whenever you're log n or anything smaller than n in terms of growth rate is learning. Okay? Another way to look at it is that this is a cumulative reward. Okay, sorry, cumulative regret, right? If you divide cumulative regret by n, that's the instantaneous regret. Okay, it's like marginal, how much regret am I incurring per round, okay, on average. Like you can see that on average, if I divide both sides by n, it's log n by n. Denominator is bigger than log n, okay, which means that as n increases, this is going to 0. So on average, my regret is going to 0 as n increases. Okay, which means that I am, which is not the case for round robin. In round robin, the regret as a function of n is just 2/3. It's not going to go down to 0. Here, it's going to go down to 0, which means that I'm learning. In other words, as I have more and more interactions, I'm playing arms as good as if I knew what the mean rewards for the arms were. Okay, because I'm competing with what's the best arm in hindsight. Okay, if I knew the mean rewards, I would always play the best one. But now I don't know the mean rewards. I'm trying out using these epsilon greedy or UCB. Epsilon greedy also has a similar claim. These types of new strategies. But after enough number of interactions, the reward I'm getting is actually pretty close to the reward I get as if I knew the answer beforehand. Yeah, let's actually take a break for 5 minutes. Okay. I want to show you what one of the Atari games looks like, so that you have better sense. If you've never played these games, this is what's called Breakout. So basically, so you basically have to balance this ball or that ball so that it kind of captures as many bricks as needed without letting the ball go behind you. Okay? So your actions are basically go left, go right, how many steps to go, and so on. So, and we'll see this maybe next lecture or the lecture after, but this can be solved using reinforcement learning. And there's an online learning aspect of it, which is basically that at every time step, let's say every second, you get as input this image. Okay, so this is what humans also see. We see this image, and we decide, okay, where to go, right? So the algorithm or the software also sees in this setting this input image, and it needs to decide its actions, left, right, and things like that, right? So take those actions, and then you also observe you're getting a reward. Okay, the reward is that score that is being tracked at the top. So obviously, in some seconds, maybe you don't see the score improving. That's okay. So based on this image, your action, feedback, triple, you need to do, you might have to do trial and error to figure out, what's making my reward go high, and actually do those actions. Okay. So obviously humans will learn very quickly that, okay, I should not drop the ball. If I drop the ball, the game ends, and I need to collect rewards. But maybe for the algorithm, you can imagine that the algorithm might drop the ball a few more times because it tries different actions, and many times the game will end, and then eventually it figure out that, okay, I need to balance the ball to get more rewards, right? So but we'll see many other, a couple of more examples next time. Okay. Let me get back to this algorithm. The, I guess, approaches we're seeing to kind of solve the multi-arm bind problem, and we've seen two: epsilon greedy and UCB. The next one I'm gonna skip for basically skip a few slides. So that's a third algorithm for solving multi-arm bind problem. Okay. So basically there are 4 algorithms in the slide deck. I wanted to cover a couple because many of them have the same idea. You need to balance exploration and exploitation. Okay, that's the key idea. And so all of these will do the same in different ways. Okay. But I wanted to kind of focus on one, at least one more algorithm, which will be needed for our contextual setting. Okay. So that's why I want to cover this one. Which is that the previous algorithms, actually those expectations and so on, that means that there is some stochasticity. There are explicit assumptions about stochasticity in the setting. Means that the rewards are stochastic, therefore I can talk about expectations and so on. But you don't have to even assume the situation is stochastic. Okay, in the sense that the rewards being collected for each action, they could have their own, different, they need not be modeled as a Bernoulli random variable or a Gaussian random variable and so on. You don't have to do that. Okay, you don't even have to assume that there is any distribution behind the rewards that you're collecting. Okay, even in that setting, you can actually design an algorithm which does as good as in hindsight what you should have done. Okay, so the metric is always the same. If you knew, all the reward patterns beforehand, there would be one of those arms would be the best in terms of, summing up those rewards, right? We don't really care about whether the rewards themselves are IID or not, or not just IID, but also they're coming from a distribution, that them being stochastic or not, we don't care. Okay. So under this under a setting which makes less assumptions, we can show that there is we can see that there is a heuristic or an algorithm that works. Okay, and that works exactly in the same idea. So you have to explore and exploit, but how do you explore and exploit is a little bit different, but it's same, very similar to epsilon greedy and UCB. Then why I'm introducing this idea is because this idea also has a guarantee, even though we are not assuming any stochasticity. Okay, even though we are not making any assumptions about the randomness that leads to the rewards, we can still get a good guarantee, that sublinear guarantee. Sublinear just means the sublinear in n number of rounds. Okay. So what is the what is the for loop? I'm just repeating the for loop, but here the for loop has a little bit of change, in the sense that, first of all, contexts are not there. That's fine, but this setting for this algorithm, for claims, okay, of how will this algorithm works, you can assume that there is an adversary, there's a second party which predetermines what the rewards for each of the K arms that you're going to play. Okay, so in the current round, think of somebody else looking at, oh, you've been doing well, let me just pick, these are the 3 rewards that you can potentially get this round. And the player, based on its feedback data, chooses something, and then because we're in the bandit information setup, player chooses the reward for the arm that it plays. Okay, that's the last point. If there's a full information setting, player sees all the rewards that it could have gotten. Okay, if it had done something else, but we are not in that setting, so let's ignore that. Third bullet point. So what did change? Okay, the only change is that we added an extra step because we have to somehow capture how the rewards are generated. Okay, we should at least say that rewards are generated by at least some player. It's called an adversary mostly because you can have some game theoretic interpretation here, but let's not focus on that. All I'm saying is that rewards need not be stochastic. Okay. So in this setting, there is an algorithm and it comes with guarantees, and this extra definition only makes sense if you want to focus on the guarantees. We are not worried about that right now. We just want to get an intuition of why how to play, how to learn, and therefore collect more rewards in this setting. Okay. So that algorithm is called EXP3 algorithm. Okay. Is just some naming that the original authors gave. Okay, and we'll see another algorithm called EXP4 for the contextual setting. So that's why they have some similar names. So what is the algorithm? So the algorithm is actually very intuitive. It just says, okay, whether things are stochastic or not, let me maintain some weights on each of my actions. So let's say the 3 actions that I have at the beginning, right? The 3 actions. So let's say for each action I maintain a weight of 1. Okay, I'll start with a weight of 1. Weight as in some sort of preference for how whether I'm going to play that or not, basically. Okay, I'll maintain a weight of 1 on each action, and then I'm going to adapt this weight. I'm going to reduce the weight, but if the action is not doing well in terms of if I take that action, I'm not getting much reward, and if the action is giving me good rewards, I'm going to increase this weight. Okay, so it's pretty natural. So how am I going to do that update, right? So before doing the update, how am I going to pick an arm? Let me specify that, because as I said, depending on the weights, I'm going to pick an action, right? So the way I'm going to pick the action to take at this round, based on the weights so far, is that it's basically just going to be the current weight for the action that I'm potentially going to play divided by all the other weights. It's just a normalization, right? I want to bring these weights, which are just some sort of preference for these actions, to a normalized situation, so that I can think of that as a probability distribution, probability mass function. Okay. So if an action has a high weight, then it will have a high probability of getting picked. Okay. If an action has a low weight, then it will have low probability of getting picked. Okay. What is this extra gamma and gamma by k? Gamma is a Greek letter. Is just to introduce exactly what we saw in the epsilon greedy heuristic. With 1 minus gamma, I'm going to rely on this ratio, and with gamma probability, I'm just going to play at random. Okay, if I'm going to play at random with gamma probability, then each action will get gamma by k probability mass associated with whether whether it will be played or not. Okay, so don't worry about this gamma. It's just to kind of encourage exploration, just like in the epsilon greedy setting. Okay, so why do you need exploration? Because you don't know what some other action could have gotten. So that's how you're going to pick an arm. Okay. Now, only thing left is how to update these weights based on the feedback. Okay. Remember, in our online learning loop, contexts are not there, so we are playing actions. This step specifies how to play actions based on weights that we maintain. The next step is obviously we'll get some feedback on the action we played. How to incorporate the feedback to improve our weights. That's the only thing left. Okay. So how we incorporate feedback is shown in a very messy way here, but what it's doing is basically weight for every arm at any given round is basically the sum of all the rewards that I've collected so far for that arm. So bracket k and k just mean for the kth arm, sum of all the rewards that I've collected for that arm, and then e to the power eta of that sum. Okay, so e to the power eta is some specific transformation, but it's just a it's actually monotonic transformation. If sum is greater, then e to the power eta will also be directionally in the same it's just a monotonic transformation. So this is how you maintain. This is how you update. Okay. But there is an interesting trick that they use, the algorithm uses. It's basically importance weighting. Okay, so the reward that is used in a sum is actually what is the original reward divided by the probability with which I played that arm. Okay, so that's a very important step in this algorithm. I mean, something that we have not seen before. Okay. So what do I mean by that? So let's say there were 3 arms, right? So let's say we played arm 1. Then for arm 1, we would have observed some reward, right? So whatever the reward is, we will have to divide by the probability with which you would have played arm 1. If the probability with which you would have played arm 1 is really small, then we're going to basically upweigh that reward as if it's an important reward. You know, the probability of playing this arm is really small. I played it and I got some reward. Let me boost whatever reward it is, and then use that in my sum to update my reward. Now for arm 2 and 3 in that round, the reward is 0. Okay? So 0 divided by any probability will be 0. So for those arms, there will be no update because the sum will not change from the previous round. So if an arm was not played, the weights will not get updated. Okay, and for arm that was played, the weight will update it because there's an extra term. Okay? So basically keep on increasing, and then to normalize them so that you're going to bring it into probability space, you have to kind of divide by weights. Okay? So why do this? We'll not get into the detail, but this effectively it has something to do with the full information setting. So EXP3 algorithm relates to another algorithm very similar, exactly the same, except it will not do this when you have a full information feedback. Okay, because the full information feedback, irrespective of arm you play, you also get information about other arms that you did not play, and so you can always update those weights even if you did not play those other arms. Okay, so this correction here is just to kind of differentiate from that other algorithm and the full information setting. Okay, I mean it has a very key role, but we'll not get into the detail. The key thing is exploration, because every arm will have at least some probability of getting played here, and also based on what rewards it collected before. And exploitation, because higher weights means higher probability of playing. Okay. So it's very similar to epsilon greedy or UCB, basically. Okay. All these algorithms have to balance. I mean, remember we are in the simplest setting where there's no context. Okay, we're not even in a supervised learning setting. So, so all flavor of these algorithms will be very similar, right? And this also has the same type of dependency. So instead of log n, there is the dependency on square root n. Square root n is bigger than log n, but smaller than n. So it's still sublinear in n, okay, which is very important. So we have to kind of have this cumulative regret growing smaller than n, or the cumulative regret divided by n, which is the kind of average regret per round, hopefully goes down to 0 as you have more and more interactions, which means that you're learning. Okay. You can always come with algorithms which like round robin, for example, will be pretty bad here. And this is showing, you know, if there is actually one of the arms which has the highest weight, which is actually which is the best in hindsight, then the weight for that arm will be increasing as a function of, you know, as a function of interactions. Now, all the 3 algorithms that we saw, the third algorithm makes no assumption about the stochasticity of the rewards, can be used even in a setting when there is stochasticity in the rewards. It's not like the algorithm has nothing to do with assumptions we're making. Obviously, if you use UCB or epsilon greedy in a setting where there is no stochasticity or there's some adversary or whatever, then they're not expected to work well. I mean, they can be used, but they may not be expected to work well. But EXP3 is, you know, has a regret guarantee even in the more like less assumption setting. So obviously, even with more assumptions, it will still work. Okay. So anyway, all these 3 are kind of in practice interchangeable, but they have different guarantees depending on the situation. Any questions here? Yeah.
Said, like I feel like it doesn't really. Like I feel like how the data is generated doesn't not. Like
yeah, in this setting for this algorithm, it doesn't matter how the data is generated. You can look at the you can see that, okay, maybe the algorithm is focusing on one of the arms. You can give bad reward for that arm in the next round, all rounds, that's fine. And the algorithm will still do well. The well part is where everything is captured, right? It'll do well with respect to the best in hindsight. So if there was an arm which was having high rewards so far, and then because now the algorithm figured that out, you give 0 rewards for that arm throughout, then that arm may not be best in hindsight anymore. Okay? But if it was best in hindsight, then this algorithm is expected to be close to that best in hindsight performance. Yeah. So this algorithm is not giving absolute guarantees. It's just saying whatever is the best in hindsight. If you mess up all the rewards so that nothing looks really good, okay, this algorithm is just guaranteeing that among the arms, whichever is the best one, I'm going to be close to that. Okay, all the arms could be pretty terrible, and because you are being adaptive, being adversarial, you're not being stochastic, so you could be messing up because you want to throw the algorithm off. The algorithm will only get thrown off as much as the best arm is thrown off. I don't know. I cut your comments out, but what was your
No, I
full
think that's,
point?
no, I was just a little confused about whether there's an adversary playing, if it matters. Like, for example, how
Oh, this matters in
interpreted what you said was kind of like how much the algorithm can recover from like someone messing with you.
Yes.
I don't really
Yeah.
know how exactly that works.
So I mean, there are situations where things are adversarial. By the way, all machine learning systems that are deployed, especially user-facing, there are people trying to kind of affect them and make them produce wrong answers and so on. So there's always going to be adversarial situations, even in the vanilla supervised learning setting. Forget about the online learning setting. So you train a model, like detecting like traffic signs. People can slightly change the traffic sign to see if the slight changes can completely make the model think that it's a stop sign instead of a go sign or something like that. So there is going to be adversarial aspects to machine learning. Supervised learning there's a whole field of adversarial machine learning for supervised learning and so on. Here, adversarial means that this algorithm makes sense even in a game setting. It's not really related to stochastic settings where you are trying to learn some random variables or parameters of the distributions governing those random variables. So it has connections to game theory and other areas. Yeah, I mean, in practice, it can be applied to in real world games, like all the rewards are not arbitrarily chosen in real world games. Yeah. I mean, it makes less assumptions. So in the real world, it's not like no user is flipping a coin and clicking a button, right? They have some complex process driving their behavior, and so if it's not stochastic, if let's say it's dynamic, it's evolving over time. It's not the same distribution of how they behave over time. For example, this algorithm, because it's agnostic to whether there's a drift in the distribution or not, it'll still do well compared to UCB and others. Yeah, so now actually we'll get into bandits with context. So which is now actually, so the previous exercise was just about trying to say there's going to be bandit feedback, and that's why we need exploration exploitation. Okay, that's the most important thing. Now we're going to try to get a little bit closer to supervised learning, but still be different, which is that the effect still persists, which is if given a context, you take an action that's not the best action. So if you cannot use that as your training data for your supervised learning approach. Okay, so you need to still figure out the best action. So for every context. So this is just a recap of the same slide from before. So there's some context, you take an action, there's some reward. Assuming that what you do has nothing to do with the next context they're having, as in the users don't get affected by your actions. Other users or the same user coming again, you need to take actions that maximize rewards, maximize expected rewards. So it's the same as before. Previous models are not enough for this, okay? Because first of all, there's context, so it's not. So what we could do is, okay, let's build a multi-arm bandit approach for every context, okay? Which doesn't make too much sense. If you could, what you could do is all the contexts that you're getting, user context, you can cluster them, and maybe there are only 5 contexts, 5 segments of users. Then for each segment, each user segment, you could have a multi-unbanded algorithm running. Okay, that's one way to kind of deal with context. So every context comes, you map it to one of the 5 segments, and each segment could have a way of what is the best action, figure it out. Okay, you could do that. So what we'll do is that essentially that, but better, more efficient. Okay. So basically, what we're trying to exploit is that whatever we learn for one context should be useful for other situations as well. Okay. What we learn about basically what we learn for one context should be useful for other contexts. What we learn for one action could be also useful for other actions. Okay, so there's some generalization aspect that we want to care about in each interaction. Okay. We already mentioned that there's no carryover effect. If there is carryover effect, that belongs to a little bit more complex problem, which is reinforcement learning. So if you think of the complexity of the problems, multi-unmanaged problem, no context is the simplest, and then the contextual bandit problem, which has context but no impact of actions on future context coming, and then the bigger set is the reinforcement learning setting where actions have impact on future context coming. Okay, so if you show really bad recommendations, user may kind of never come to msn.com or may not open YouTube if the YouTube recommendations are pretty bad, right? Yeah. So what's the contextual learning problem? I mean, it's the same thing. Every round we get a context. We want to find now, we want to take the best action every round, but because we have a context, we're going to talk about what is called a policy. Okay? A policy is going to be a mapping from a context to an action. So a mapping just means a function. So what we want is we want to find the best function that goes from a context to an action. Okay. Now this resembles supervised learning. The supervised learning is all about mapping from inputs to outputs. So it's very similar. So we can think of the policy as like a prediction function if you want. But the important thing is you will not see the same context twice, and you still have the bandit feedback going on. So you don't know if some other action would have been better. Okay. Obviously different from multi-unbanded settings. MAB stands for multi-unbanded settings because there's no context in that previous setting. Okay. And in those settings, we were only finding the single best action. Remember, one of the arms is the best. Here, depending on every context, different arms could be the best ones. So it's more complex than MABs, right? Because there's so many contexts. For each context, there's a best arm. So how do you find that? Right? So obviously, we need to rely on generalization. So here's an example of benefiting from context. Okay, this is just an illustration to get a sense of there has to be some generalization. Like you have to learn something that's not only useful for the current action that you do, but also helps something beyond that. Okay, so let's say we have 5 ads, and I'm going back again to marketing situation, advertising situation. But let's say we have 5 ads. These are the 5 ads, A1 to A5, and let's say we have 4 policies. Okay, for simplicity, what do I mean by 4 policies? Let's say I only have 4 functions which go from context to actions, and I'm only interested in figuring out which one of these 4 policies is the best one. Okay. Why 4? Why not 40? I mean, it's the same answer, 4 or 40 or 400. But let's say we have a fixed number of functions. Now, this doesn't make sense for even if you're doing linear regression, you have an infinite number of functions, so that doesn't make sense. But let's say you have only 500 decision trees that you care about. Okay, or maybe only a very fixed number of functions that you care about. Your predefined neural networks that you care about, for example. Okay. Now let's look at one round of EXP3. Okay. How can we use EXP3 here? Is because you can think of 4 policies or 4 policies as 4 arms if you want. Okay. Because once you pick a policy, the policy will tell you what ad to show. So it's like at the policy level, if there are finite number of policies, you can just play EXP3. Okay. So let's say in round T, this is what the policies recommend. Okay, so in round T, EXP3, remember we have to choose one of the policies, right, with some probability and play that policy. Playing the policy is essentially saying what was the ad that the policy recommended and show that ad. Okay, so let's say there were 2 policies that are planning to show the same ad, suggesting the same ad for this context, incoming context, and then two arms or 2 policies that are showing the same ad for some other same ad for this context. Okay, so let's say, so this is the situation. Like but we have we are maintaining a distribution of policies, right? Remember, exp3 means distribution of policies, distribution of arms, and let's say we get to choose arm E1. So we just chose arm E1 from that figuring out which arm to play, and we play that arm. Okay, which means that we play the add choice that that policy says. Okay, so which is A2. Now, obviously, if we played A2, then we'll get some reward, maybe $1, maybe they clicked on that ad, or maybe they did not. We'll get some reward, and exp3 had that division by the probability with which you play that arm. Okay, so that's fine. We got some reward, and we'll update the weight for that policy. Okay, and rest of the arms all get reward 0, which means rest of all the policies get reward 0. But we noticed that even if we had chosen the second policy, we would have gotten the same reward, because it would have shown the same ad. So it makes sense for us to actually update the weight of the second policy as well. So there's a little bit of generalization going on here. So so E2 is also recording the same E2. So we should better estimate the reward of E2. Okay, so that's that way you are generalizing beyond exactly what you played. So in the given context, even though you played one policy and you got some reward, you are actually updating the weights or importance, or some sort of your sense of how other policies do with the same observation. Okay, so you're generalizing beyond the policy that you learned, beyond the policy for which you got the reward. Okay, so that is a element which is not there in exp3, and so we slightly modify exp3 to make it to capture this, which is called exp4. It's exactly the same as exp3, except now we have a distribution, we have a weight on policy. Policies are generally represented by the letter pi, okay, the Greek letter pi. So we're going to maintain one number per policy. That's why we had 4 in the previous illustration. Okay, we'll maintain one number for policy, and we observe a context. Okay, this was not there in exp3. We just were playing something every round because there was no context. But in this round we have context, and so for that context we'll look at every policy that predicts a action A. Okay, so we have capital K actions. Let's say those 5 ads. So we have 5 actions. Then we'll basically group our policies into, okay, these policies are predicting the first action, all these policies are predicting the second action, all these policies are predicting the third action. Okay, and so what is the probability of an action? Is just all the weights of all the policies which are predicting the same action divided by all weights. Okay, so it's basically saying, hey, if there's a in the given the current context, different policies are saying predict these actions, predict these capital K actions. So for each action, I'm going to aggregate the mass of weights, or the sum of the weights that I've assigned to each of these policies. So maybe, for example, the first action, there are 10 policies that are all predicting the first action. That means I'm going to just sum up the weights of these 10 policies, and that's going to determine the probability with which I'm going to play that action, the first action. It's just some sort of aggregation. For each action, look at all the policies that predict that action, and take the weights. Okay, that's what the numerator is doing. Denominator is just the sum of all the weights, the same as before for exp3. And then the reason there is some gaps is because there is just like gamma in the previous slide is the same as gamma effect. So don't worry about the p-min stuff. It's just you need to have some exploration. Remember, this whole binary feedback means there's exploration needed. Okay, so p-min, don't worry about the expression. And then you draw an action from this distribution of actions, collect some reward, and then you do importance sampling. Do that importance weighting while updating the reward. So R divided by the probability with which you played the action goes into the weight update. So previous weight times e to the power R divided by the probability with which you played the action. And for others, it just remains the same weight. So I know the notation is a little bit different, but it's the same as exp3, except you're doing an aggregation over all the policy weights that are predicting the same action. That's a change. Okay, so it turns out this algorithm is a kind of algorithm, pretty inefficient, because it's basically maintaining one weight over policies, and so which means you'd have to have enumerated the number of policies, which is not true if you have number of policies being infinite or something. Okay, This is a canonical example of a model of a algorithm that we can see. Now, this algorithm looks very, very different from supervised learning. Right? It's not even close. There is no. They are literally enumerating each function that goes from context to action and maintaining weights on that. Okay. Whereas in supervised learning, you would have a context, comma, best action to take, some tuple pairs like that, and you would learn a function which goes from given a context, what's the best action to take. Okay, and rely on generalizability. If there's a new context, hopefully the function generalizes to the new situation and also produces a hopefully a good or best action. Right. So that's what supervised learning would get you. But we can't do that because our feedback is banded. Okay, our feedback is banded feedback. We only get a reward for what we did, the action that we took. We don't know what would have happened if some other action was taken. Okay, we don't know. And so, given this banded feedback, you have to do something more. Okay, this is not the only algorithm. There are many algorithms for both multi-arm bandits and contextual bandits, but I wanted to show you an example of an algorithm very similar to the EXP3 algorithm for bandit situation. Okay. Any questions? Yeah.
It's going back a lot. Sorry about that.
That's fine.
What is the context?
Context is the feature vector. So the user profile, for example, let's actually not worry too much about the when users arrive on the website, right? All their browsing history, the user account, previous users, that's a feature vector, the context of the situation. In this situation, I need to take an action, right? Which is what articles to line up here. Maybe I'll have thousands of articles, but I only have space for like 22 things to show. What are the 20 things out of the 1,000 things I can show, right? So there is some policies to say, hey, given this context, these are the sports-related items, these are the music-related items, and then user response with feedback for the things that you showed and not for things that you didn't show. Okay. Anything else? So let's wrap up pretty much there. I wanted to stop at this slide and we'll cover other things later. But today's objective is actually, it's a she shift from previous lectures, right? Unsupervised learning or supervised learning. So what we want to do is really look at some type of decision making. Okay, decision making is a broad area. We saw complex decisions, which are just static decisions. Even if there is no online component, they were hard. They were not just a direct mapping from predictions to decisions, inventory management or other things, routing of trucks, or even Uber. Like Uber, when it solves matches, service providers to the people requesting rides. It's an optimization problem. It's based on demand forecasting and the willingness to pay and many different things, delays and so on. Right. So there's so many complex decision making problems. Now, what we are looking at is one type of a situation where there's a way to get feedback for your actions and then improve your actions. So there's a repeated interaction in a situation. Like so the inventory management setting, it's like, hey, order the inventory this week, order the inventory next week again, and so on. Maybe there you can learn from, hey, I took these decisions, I missed out on sales, or I took these decisions and I got stopped out, okay, midweek, right? So those are feedbacks based on which you should improve your decisions, for example, right? Anyway, so coming back to the high level picture, we saw that in these types of online settings, because of banded feedback, you can't just apply supervised learning. Okay, so you will have to do more to kind of deal with supervised learning. You can be sample inefficient. As I said, you can just do round robin and try everything, and so that you know what the best is, and you log that information, and then you can learn. But that's too inefficient. So we said, okay, let's start with a situation where there's no input feature vector or no input context. Okay, in that situation, because of the stochasticity, I can't just do every action once and then figure out what the best action is. I'll have to try things again and again and again. For every action, I get a reward, stochastic reward, and I want to kind of collect these rewards as to minimize the cumulative regret. Okay, and so I need to be adaptive. I need to be dynamically focusing more on the more promising actions and less on the less promising actions. That way, I can minimize the cumulative regret. We saw 3 algorithms: epsilon greedy, UCB, and EXP3. Then towards the end, it's a very quick treatment of contextual learning where you have a state or a context. So I'm again introducing a new word here. State and context mean the same thing as a feature vector. Given the feature vector, I need to decide an action, and both the feature vector and the action together influence what reward I get, okay? Because the feature vector could be of the user, and the user sees what action I took and maybe gives me a reward. So in this situation, how do I deal with, maybe context don't appear, maybe never repeat, for example, that can happen. So how do I, learn and show better, take better and better actions in different contexts, right? So this has to be some generalizability, and we saw one version of the generalizability where if one policy gets a point, then other policies which are also predicting the same thing get also get a kind of a reward, and so that way you kind of also minimize regret. Okay? So that's contextual bandits. Now we haven't talked about reinforcement learning at all, and I will not mention it beyond this one sentence, which is there's one extra arrow here, which is that what you do, what actions you take, influences what new contexts or what new states happen in the future. Okay, so if you show bad recommendations today, as I said, 10 a.m. for this user, then when the user comes back at 10:30 a.m., they remember that you showed bad recommendations before, and that will influence your reward as well. Okay, so maybe they were in a happy state when they came to your website, for example, msn.com. You showed bad recommendations, then your action influence the future state in the sense that maybe in the future they are, disinterested when they come to your website. Okay, so I mean that's just one example, but next time we'll see many examples like this. Okay? And the breakout game that you showed is exactly this, right? So your action influence the future state. If you are able to balance the ball and able to hit it back up, that will influence the future state, because future state some bricks may actually vanish because you were able to balance the ball. Right, so your actions influence the future states, where states are now the screenshots that the screens that you see on the game. Okay, so we'll talk about that more next time. So let's end today.